I am Suzanne LaGrande, and this is The Imaginary Possible, a show that looks at the captivating potentials and the troubling realities of artificial intelligence today. For the last 10 weeks, we've been discussing the implications of artificial intelligence from a variety of perspectives: how AI is changing the nature of work and how we go about getting a job, how educational businesses and ordinary people are using chatbots, and some of the ethical questions that arise as we rely upon artificial intelligence to replace many of the jobs formerly done by humans. In this episode, we're going to step back and look at the early history of artificial intelligence and how it evolved. My guest today is Rudd Canaday, who is a computer scientist, software architect, and writer. Welcome.
Hi.
Rudd wrote his first computer program as an undergraduate in Harvard in the 1950s. You were really at the forefront of developing computers and computer science, really before there was a science. How did you get interested in doing this before this field really existed?
Well, somehow it was a very straightforward progression. As a small child, I was really interested in electricity, and I learned Ohm's law and things like that when I was 9 or 10. And then actually in high school, I discovered electronics. And somewhere I ran into a book, I've never been able to find it anywhere, written by the guy who invented the Bell Lab's first computer, about how you can use relays to do digital logic. So that way I discovered what digital logic is. I also found the place where the telephone company threw away all their old stuff. Wire was $1.50 a pound. So I actually built some things using digital logic. When I went to college, my second year there, which was 1956, they got their first general purpose computer, a UNIVAC Scientific, and they offered their first course in programming. So I took it. I think I've been hooked since I was 2 years old. It was a very straightforward linear progression, never any deviation.
But how interesting, because really you were studying things that were really being developed as you were studying them, and you were part of that development.
Yes.
After you graduated from college at Harvard in physics, you went on to MIT. And there you studied with Marvin Minsky, who is one of the first computer scientists who focused research on artificial intelligence. And this again is in the late 50s, early 60s, right?
Yes, I wrote my master's thesis under Marvin Minsky in 1962. And actually, Marvin Minsky not only was involved in it, he was the leading person, I think, in the world in artificial intelligence at that point, and had an artificial intelligence group at MIT, one of the very first. I think there might have been one also at Berkeley. I decided to write my master's thesis under him.
What was artificial intelligence in this time period? How were people thinking about it?
The group that worked with students who worked with Minsky were very enthusiastic, and they thought in 5 years, maybe 10, we would have machines that could learn and really be what we would call artificial intelligence. They were completely and utterly wrong.
And why is that?
Well, in 1960, 2 years before I finished my thesis, there was work being done on something called a perceptron, which basically had the right idea, namely that you have nodes that are interconnected and the interconnections have weights on them. And that's really the way our AI works today. But with the hardware available at that point, 1960, 1962, it was an impossible job. So they actually built a piece of, this was not at MIT or Berkeley. They built a hardware machine, a machine to do basically a one-level learning algorithm using the modern technology, but one level. We all considered it a joke. We thought it was entirely the wrong approach. And Minsky in 1969 Minsky published a book that talked about this and said that he could prove that the one level perceptron would not work. And there are significant things it simply couldn't learn. And he was right. And people thought he was saying that perceptrons won't work. It's not actually what he was saying, because he thought maybe if you could have a lot of levels, it might work. But it was obviously impossible to have a lot of levels. It was so difficult with one level that they had to build special hardware to do it. And so actually, if I had stayed in the AI area, I would have wasted my time for a good 20 years, because nothing happened. No approach worked. Nothing worked until in the 80s that people started using the idea of nodes that are interconnected by weighted connectors. And it's basically a model of how the human brain works. In some ways, a crude model.
So can you help us who are not computer scientists to understand what one level of perception means in terms of AI and why that was a limitation?
I have to do a disclaimer right now that really I have not studied AI since the 1960s. I'm not really up on it, but basically the way it works is the way the brain works is that you have neurons which are connected by axons. And as new information comes in, the brain breaks down some axons and adds new axons. So we have this incredibly complex interconnection of neurons connected by axons, and the connections and the neurons too come and go. So it's very dynamic, and it basically reshapes itself. And an important part of that reshaping is the connections between the neurons, between the different neurons by the axons. What artificial intelligence does is sort of mimic this in a way that can be done on computers. You don't have a zillion neurons that can keep come and go. You have a whole lot of, I'll call them neurons, units that are interconnected by connections that don't come and go, but they're permanent connections. They're basically all connected to each other, but there's a number with each connection that says how strong that connection is. And somehow this learns. But if you only have two layers, one set of neurons connected to another set of neurons, and that's it, it can't learn. Modern machines are about 5 or 6 levels, I think.
So this is what people now call neural networks.
Neural network. And the thing in the brain is a neural network too. And that works, but it only works if you have huge amounts of computing power. And today you have entire buildings full of computers that require power substations to run them, all interconnected. So it takes a huge amount, even by today's standards, a huge amount of computing power. Back in the 1960s, it was just impossible. It was a ridiculous idea.
So the problem was not that people didn't have the idea of how to do it, but they didn't have really the hardware or the mechanisms to be able to do what they could see might be possible. Is that right?
Not really, because the mainstream AI community, for example, Marvin Minsky at MIT and people at Berkeley, dismissed this as a ridiculous idea. They simply thought it would never work. They didn't think it was just a matter of computer power. They simply said it's a bad idea. It won't work.
You know, Minsky's book, I think it was about perception, kind of initiated what they called the AI winter, this period where AI was kind of not being developed because they didn't think it was possible.
Oh, no, that's not true at all. AI was being developed, but not using the perceptron model. And that just doesn't work. So like 20 years were wasted trying to do AI, trying very hard to build AI systems, but they didn't have the right model. And so nothing worked. I could have done my PhD. In fact, Minsky asked me to do my doctorate in AI under him. And I could have done that. And I could have spent 20 years working on AI and gotten nowhere.
But now instead you did get somewhere, because after you graduated from MIT, you went to work at Bell Labs.
Yeah.
And
I have a little interesting story about that. That's something I just think I realized when I was thinking about this talk. Is the reason I didn't go on and do my doctorate with Minsky was because using computers at that time was so incredibly painful. You have a deck of cards, you submit the cards, which are your program, you submit the cards, and 24 to 48 hours later, you get the results back and discover I put a comma in the wrong place and the entire run is worthless. I made a vow to myself that my doctoral thesis would not involve using a computer. And I did that. And so it wasn't in AI. But after that, in my career, I invented 3 different systems that make it much more easy to use computers. And I'm wondering if that isn't why. But anyway, I abandoned AI because of the difficulty of writing the programs.
So can you talk a little bit about going to Bell Labs and why Bell Labs was at this time a place where computer science was being developed or innovated upon?
Because I discovered I couldn't really combine teaching and research. If I was doing teaching, it took away from the research. If I was doing research, it took away from the teaching. But I decided, because I had experience teaching at MIT, that I needed a non-teaching job.
You did many things at Bell Lab, but one of the things is that you worked along with Dennis Ritchie and Ken Thompson on the initial design of the Unix file system. And Unix and Unix file systems continue to be the basis of most operating systems on our computers and smartphones. Could you talk a little bit about how that came about?
All right. A recruiter came to MIT and recruited me for Bell Labs. And so I told him I wanted software, even though my doctoral thesis was in hardware, I wanted to work in software. And as soon as I got there, they said, nobody told us that. So they scrounged around and managed to find a job for me, not in research. I didn't realize it was not a research job. I didn't know there was such a division in Bell Labs between research and non-research. They found me a job in the military area. And so they kind of sat me behind a desk and had me start reading all these classified documents. I was bored out of my skull. I went to my boss and I said, what we need is a time-sharing system on this military hardware so people who are writing programs can do it on the time-sharing system. And he said, oh, and I said, but before we try to develop it on the military hardware, we need to develop it on a conventional computer. And so he said, okay, and he assigned 7 contract workers to me and set us up above a strip mall. And so I had 8 people above a strip mall and nobody cared what I did. So I built a time-sharing system.
What is a time-sharing machine?
Back when even a relatively small machine cost, $1 million or $100,000, a lot of money, even for a small one, you couldn't have just a machine of your own. So what a time-sharing system does is allow a number of people simultaneously to use the computer. And initially, it was just using literally a teletype machine. You type on the machine and it prints on paper and it's connected to the computer along with 10 or 100 other people on teletype machines, all doing their work, not software, whatever they're doing with the computer. So that meant you had sitting in your living room a teletype machine, which was in effect a personal computer. When I finished the time-sharing system, I had a job offer from GE for the contractors. And so I went to Bell Labs with a job offer in my pocket. And I said, either you transfer me into research or I go to GE. Now, almost nobody ever was able to transfer into research because everybody wanted to be transferred into research. At the same time that I went into research, 2 department heads and a director went from research into the place I had been. So everybody said it was a baseball trade. Me for 2 department heads and a director. But I ended up then in the computer science, rather small, I suppose 12 people or so, computer science part of Bell Labs research with Ken and Dennis. And we were working on a time-sharing system called Multics, and we all realized it was never going to work. And so Ken said, I'll bet we could build a time-sharing system on a small machine. And so we did.
And that was Unix.
Yeah.
Can you talk a little bit about what happened after that with Unix?
Yes. Well, we got to the point where we needed a computer. Now, we were in research, which meant we could do anything we wanted, literally, we could do anything we wanted. But if we needed hardware, if we needed to spend money, we needed approval. At this point, everyone realized that the Multics project, the big time sharing system everybody had been working on, was a failure. Ken, Dennis, and I went, I remember this vividly, sitting in the director's office and saying, we need a computer. And he said, I can quote almost verbatim, he said, Bell Labs was badly burned by Multics. Bell Labs is never going to build another operating system. So I left. Ken and Dennis went to the patent department and said, if you buy us a computer, we'll build something that'll do your paperwork. And they got the computer. But I, believing the director, the executive director actually, left and went to another part of research, which was just starting up, and formed a new department. I was the second youngest department head ever at Bell Labs.
How would you characterize how these kind of new discoveries and inventions in computer science actually got developed?
Well, I think Unix is a pretty good example. It was an idea of Ken Thompson's. Ken Thompson said, this Multics thing is never going to work. I'll bet we could build a time sharing system on a small machine. And Dennis and I said, oh, great, let's do that. My next department, one of my coworkers, had an idea about how you could use a computer to do database management. It's called a backend or database server now. And no one had ever done that. And I said, that sounds like a good idea. So I put together a team of 4 people and we did it. I think every significant thing that I've worked on, what's happened is that somebody's come up with a good idea. I've seen that it's a good idea. I put together a team of people and we've done it.
So there's something here about how teams work together that also makes that possible.
Of course. In fact, I believe my success is not because I'm any good at research. I'm really good at running teams. And I'm good at spotting good ideas. And if you do those things, you'll be considered a really brilliant researcher.
And what was it that enabled you to create good working teams, would you say?
I think it's called type A management. You believe in the people who work for you, you trust them, and you support them, and you don't manage them. You provide a good environment for them, and they manage themselves if they're any good. If they're not, you get rid of them, which I rarely had to do.
So it's about trusting people to be creative.
It's not just trusting them, it's letting them do their thing. Don't get in the way. Support them. I had one guy who worked for me who was a brilliant mathematician. And every day at the end of the workday, he would come in and we would sit for an hour in my office and he would describe what he's doing on the board. And I would struggle to try to understand what he was saying. And I would kind of think I maybe understood a little bit of it, but not much. And so I'd make some comment or whatever. When he left for another job, he said, I was the only person in the department who really understood what he was doing. I didn't have a clue.
But you let him do what he was going to do.
And I supported him. And I listened to what he said, and I was interested.
From this period now, which is, some 50 years later, where we've gone through this entire computer revolution and revolution in internet, and now we're on the brink of a revolution with artificial intelligence. What kind of things do you think made this evolution possible?
An awful lot of it was the strength of computers. The development of integrated circuits, first of all, of integrated circuits, and then getting faster and faster and faster. So the machines become more and more capable. So then the people who are writing programs for them are more and more ambitious. And the tools for writing programs get better and better. Mm-hmm. I think a lot of it simply has to do with computer power, and certainly AI, which takes huge amounts of computer power. You couldn't have done it 20 years ago. I don't think you could do it 10 years ago, not the way we're doing it now. Yeah. So that's a lot of it. It's just the evolution of the hardware, and then the people will take advantage of it.
What concerns do you have about how AI technology is being used or will be used moving forward?
There's an interesting example I heard recently of a lawyer who used AI to create the brief for the case he was in, and the AI gave him 4 really brilliant examples of similar cases, and he used this in court, and it turned out all of the examples were completely false, and he was disbarred. And he said, and I think this is the significant part, he said, I didn't know computers could lie. People trust the machine. The machine has no morality. People, they're beginning to use AI in warfare. And I think the problem is people don't realize that, first of all, it has no morals one way or the other. And secondly, it doesn't even know what lying is, so it'll do it quite cheerfully, but people believe it. And I think that is the fundamental danger, that people will believe that AI is correct without using their own common sense.
Do you think it's possible to program computers to have an ethical or moral sensibility?
I think that's a really, really interesting question. I don't know enough about AI, really. I don't think anyone knows enough to give a definitive answer. I think the answer is right now, no. We don't know how. That doesn't mean it wouldn't be possible. But since one of the reasons that an AI machine with far fewer neurons and far fewer levels than the human brain is getting to the point where it can equal or surpass the human brain in some tasks, is just because it has access to such a huge amount of data, the entire internet, really fast. So it can look stuff up that would take us 2 hours to look up. It can look up in a fraction of a second. It's all that information, but there's nothing on any of that information that labels what's true and what's false, what's good and what's bad. There's nowhere for the computer to get a moral compass, because it can't get it by reading the internet. People get completely bamboozled by the internet. You can't expect a machine to figure out what's true and what isn't, what's good and what's bad. So where is it going to come from? I don't know.
You have such an interesting perspective of seeing how our world changed as a result of the evolution of computer science. Looking back at how much the world changed, do you have any insights about what we should be thinking about, given what you've seen happened?
Entirely, it's about ethics. Entirely about how do you avoid the bad. Look at the chat, the social media, which are full of lies. Look at the internet, which is full of lies. I recently got a valid certificate for my dog, but if I went on the web, all kinds of certificates were offered for a price, and nobody realized they're completely bogus. So, and all the stuff that's going, all the lies. I think that's so the whole issue is the internet. It's not computers.
It's how we assess the information that computers are delivering.
The internet isn't computers delivering information. It's people creating information for other people. It's not a computer problem.
It's a people problem.
It's a people problem.
Yeah, that's fascinating.
And now computers have created this people problem, but computers are not going to be able to manage it. I don't think so. I don't know. That's how do you build ethics into the computer? I don't know how to do that. The computers have built this system that allows this huge explosion of misinformation, but they're not responsible for it, except for creating the internet.
And it's humans that are going to have to solve this problem.
I don't see any way to write a computer program that enforces ethics, because whose ethics will it enforce?
Today, I've been speaking with computer scientist, software architect, and writer Rudd Canaday about the early evolution of artificial intelligence and computer science. If people want to find out more about your work and writings, where can they go?
Well, I have the advantage of having an absolutely unique name. If you Google Rudd Canaday, you get me. You might have to look hard to find the fiction that I write, because I write that under the pen name Alex Head, and there's other Alex Heads. But if you go to Amazon, like Kindle, and look for the author Alex Head, you'll find me. But as far as my career goes, all you need is Rudd Canaday. You'll get my website, you'll get 2 Wikipedia articles, little ones, and you'll get about 10,000 references to Unix.
Thank you so much for being on the show today.
You're welcome. Thank you.
You're listening to The Imaginary Possible, a show about the captivating potentials and troubling realities of artificial intelligence today. I'm Suzanne LaGrande, and this is KBOO Community Radio, KBOO 90.7 FM in Portland. To listen to this and other episodes of The Imaginary Possible, visit us online at kboo.fm or theimaginarypossible.com. Thanks so much for listening.